Okay, so thank you for doing this. We're very happy to extend the Monnier on economics and that about the global gravitational anomaly and structural fields.
Okay, thanks. So thanks to the organizer for this meeting, and thanks to you for doing this. So yeah, some more doing this. So let me just remind you what is the stability theory. So it's just an abelian 2L form DH theory, which is on a 4L plus 2-dimensional manifold. And those 2L plus 1 form constraints obey a stability condition. So for instance, you have the chiral boson in 2 dimensions, which is on the vortex of the center of the string. You have the field like this on the whole volume of the Ethereum type 2 wave brain, and the Raman 4 for the field in type 2 So the global gravitational anomaly theory is still unknown, somewhat surprisingly. So it is foundational paper of gravitational anomaly. We can make some heuristic proposal, which is valid only when the middle-dimensional cohomology of this manifold vanishes. So our aim would be to get the formula. This is a somewhat important problem. Imagine that you're taking some random background with time brain, then you might want to check that it's not anomaly. So, of course, I won't have time to introduce you to all the subtleties of this theory. So, as there also might be some mathematicians, I'd like just to tell you some. What I believe is a nice mathematical story, and hopefully in the end you'll see So let's start with the Riemannian manifold of dimension 4L plus 2. And in this dimension you have some pretty specific properties. For instance, the exterior product of the form combined with integration gives you a symplectic structure of form of degree 2L plus 1. And the Hodge-star operator on square to minus 1 in this degree, so it defines the complex structure on the space. And this structure restricts to the harmonic form or equivalent of the common. So, in addition to this, we'll endow our manifold with an extra structure, which is a quadratic refinement of the intersection product on the integral value common. It just means some function to Z2 which satisfies this equation. And if we choose two Lagrangian subspace of this space and decompose our arbitrary integral form like charts like this, then it's easy to see that all these quadratic refinements are classified by simply a vector in H with plus 1. And that any two vectors that differ by an even class with the irreducible. Now, we want to consider the manifold of all Riemannian metrics on X, and also the group of diffeomorphisms that will preserve all of these quadratic refinements. Preserve the extra structure on X. I want to form the quotient. So in general, this is a very singular case because you have some metrics which are symmetries. But we can get a smooth quotient simply by respecting the diffeomorphism group to the diffeomorphism which preserve a point and its tangent space. So it's a nice exercise to check that this indeed is okay. And so our story will be about trying to construct line bundles over this. So we'll discuss 4 methods to construct line bundles. The first method is pretty done, simply by Kuhlbach. The idea is simply you find some finite dimensional space on which you know a lot of bundles, and then you come back to our complicated space. So to do this, we can so the action of our diffeomorphism group induces an action on the harmonic form by Kuhlbach. And this action is symplectic with respect to omega. It also preserves the integral structure of omega. And you can show that it factors through the integral symplectic group. But if you consider only this diffeomorphism which preserves our extra structure, it factors to the level 2 congruent group. That simply the kernel of the reduction module. Take an element here and reduce the kernel of this map. And the Hodge star operator also restricts to the cohomology. And it defines actually a polarization of the cohomology. So it defines a point tau in the single upper half plane. So this tau is basically a complex symmetric matrix with positive definite imaginary tau. So we see that from this data we have a map from this infinite dimensional space to finite dimensional quotient, the single upper half plane, by this the image of the group. So luckily, the line bundles over this modular variety have been classified recently by Gutmann in result of Tato, at least in the case where the dimension of the cohomology is larger than 6. So here is the result. So this is the free part, this is the torsion. Just generally you have a lot of flat line bundles over this space. And this can be simply, this map can be seen as taking the term character in the complex model. So what is nice is that the trivial modular form can be seen as section of line bundles over this space. In particular, the weight of the modular form is simply half the image of this one. So what kind of modular form do we have? So obviously we have theta functions. So here we are considering any theta constants which are theta function evaluated as essentially the origin of the abelian variety. So this theta function depends on the characteristic, and notice that the characteristic is exactly the same data as this quadratic refinement that we define on the mid-dimensional cohomology. It's basically an integral vector modulus 2. And this bundle generates the integral modulus 2. Now, K will be the determinant bundle of the first bundle, whose fiber is simply the maximal exterior product of the cohomology. We can show that the corresponding modular form has weight 1, so the image of this is 2. So after we can construct some flat bundles simply by taking the square of the bundle like this, and the inverse of this one. This is a flat bundle, and you can explicitly compute from the transformation formula we tested the theta function what is the character which characterizes this flat bundle. So remember about these bundles, we will come back to that. So this was our first method. The second method is related to families of direct operators. So we can construct this fibration where again this works obviously on these two factors by metric and by definition of X. And so we can see a Dirac operator D of X as some family of Dirac operators parameterized by our infinite dimension manifold. And this family has a determinant bundle D, which is a line bundle over space. And it's endowed with some natural information structure on the wall. So we will choose a specific Dirac operator, which is the Dirac operator over to chiral spinors. So it can be seen as mapping the even cellular form on X to odd cellular form on X. So in terms of spinor bundle, it acts like this. Then we can show that this determinant bundle, in fact, is orthotic to the inverse of this bundle K, which was the determinant bundle of the first bundle. So more precisely, it decomposes into two parts, one which is due to the zero mode of the Dirac operator, and one which is due to the non-zero mode, and this part is topologically trivial. However, even if it's topologically trivial, its natural connection and permutation structure of the natural connection on this bundle. So using work of between Fried and the German thinker, we can get actually a formula for the connection, the anomaly of the connection along the group in this case. And it reads like this. So So very briefly, if you have a loop like this, you can construct a mapping torus from X. So you take X times an interval and you identify two ends with the corresponding diffeomorphism, corresponding to gamma. And you take B, a manifold that bound this mapping torus, provided it exists. And then the anomaly formula reads like this. So sigma B is just the signature of B. 2H is the dimension of the space of cellular form which are left invariant by the diffeomorphism. K is the Roger characteristic of X, and L is the L-gen of X. So what's important is we have a holonomic formula for this with the holonomic element. So this was our second method. The third method is the work of Hopkins and Singer, which is quite elaborate. So I will completely simplify very much by just saying that they construct a line bundle on the base of any fibration for n plus 2 manifold equates roughly with the metric and refinement of the quadratic refinement of the intersection term. So if we apply it to the same fibration, we have some bundles for eta, which is again it will depend on this refinement. And they also give us a holonomic formula for this bundle, given like this, where lambda square is some cohomologic class on B. So again, B is some manifold bounding to mapping torus. And this class depends actually on this So like before, we can form a flat bundle with R, eta, and so B. And simply by combining the two formula, this formula and this one, we can get the formula for the holonomic bundle. This was our third method. So the fourth method is maybe the most fancy one for the mathematician. So the fourth method is to use the quantum field theory. In general, the partition of function of a quantum field theory defines a section of a line bundle over this space. So if this bundle is not canonically trivialized, physicists say that there is an anomaly. So there is different level at which we can analyze this anomaly. So at the topological level is just the topological class of the anomaly bundle. Well, this bundle always comes with a natural connection. So the local anomaly is the curvature of this connection. The global anomaly is the set of anomaly of this connection. And if both of the local and the global anomaly vanish, then the anomaly bundle has a canonical trivialization, and then you can really see the partition function as a honest function. This is, for instance, necessary if you want to study the problem of gravity. You want to sometimes to integrate over this state. And do this only if it is real. Okay, so now, of course, we have our theory, self-relative theory. It will provide us with some bundle that are equal A, eta. The self-relative theory obviously that's why I introduced this concept of depends on this quadratic refinement, so the anomaly bundle of and so what has been known for a long time is that the local anomaly for a pair of cellular fields coincide with the anomaly of minus 2. This means that modulo torsion as bundle with connection, these two bundles are the same. So when I write three equivalent between equivalent as bundle with connection, this is what topology is. So the main result that I show recently is that topologically anomaly bundle is equal to this bundle C theta. Remember, this was the pullback of the theta bundle from our finite dimensional modular array. So this is proven essentially by using an action for a pair of cellular fields using explicitly the path integration, and then using some more fancy argument for other fields. So with this, you get information about the square of the bundle. Check that the square will. So, well, this is the main result. So what I will say is not quite completely very verified and probably right module consistency. So what we really want for physics is a formula for the anomaly, because we really want our bundle to be canonically trivialized. And even if, for instance, if we knew that that combining this theory with other theory we get trivial bundle, it's still not sufficient to guarantee that there are no anomalies. So remember that we have the relation like this topologically. We can construct a natural connection on. We can deduce that the natural connection on this bundle actually is the same as the connection there. So using the anomaly formula that we know for this bundle and the anomaly formula that we know for this bundle, we can get the formula for the anomaly there. So the anomaly of the flat bundle is just given by this character of the level 2 congruence group. And this was the anomaly formula for D-1 that we wrote. So first, there is two problems with this formula. First, this gives you only an anomaly formula for the square of the anomaly bundle. So what you really want is take some square root of this formula. And this, of course, this is a circular valued function, so it's really not so useful. We can take the square root. And yeah, normally it's not very nice formula. So now, let me tell you about two conjectures that they might be naive. But the conjecture is that the anomaly bundle is actually equal to this bundle construction by Finger, at least topologically. I'm pretty sure that this is true. A stronger conjecture is to say that these two bundles agree when considered as bundle with connection. And if this is true, we can express this flat bundle like this, and as a result, we get a formula like this one. So remember, we computed the holonomy of this flat bundle and given the expression. This is just the logarithm of the character of the electric congruence group. So the idea is to try to check this formula. It's not so easy. And if this formula were true, then the Hawkins-Singer formula provides us a formula for the global gravitational anomaly theory, which reads like this, where lambda was this class which depends on topology prefix. And you can see that this formula is consistent, because if you evaluate it, for instance, on a closed manifold, you can show that this is an integer. So this anomaly formula, for instance, does not depend on the and yeah, so this is the idea to check this relation. And I'm not going to. Okay, so here is summary. So we determine the topological anomaly of the circular theory, and yeah, we have a conjectural formula for the global anomaly.
Questions?
Super nice question. So this was all about the dependence of the relation on the metric. There's also a story with the fine grain theory about the dependence on the C field.
Yes.
Does that story interact with this one?
Yes, we should interact, especially in the another reason to believe this Singer formula is that here we have automatically in this class lambda you can include this C field. And this, we already know that this formula correctly describes the anomaly associated with C field. So it looks like
Thank you, Steve, again.